Hello everyone, and thank you for attending today's webinar, Background Modeling and Non-Ideal Sample Analysis. Before we begin, I'd like to cover a few housekeeping items. At the bottom of your audience console are several application widgets you can use. If you have any questions during the webcast, you can click the Q&A widget and submit your question. We'll try to answer these during the webcast, but if a fuller answer is needed or we run out of time, you'll receive an answer later via email. We do capture all questions. A copy of today's slide deck is available in the Resource List widget, which looks like a green folder. You can expand your slide area by clicking on the maximize icon on the top right or by dragging the bottom right corner of the slide area. If you have any technical difficulty, please click the Help widget. It's a question mark icon and covers most common technical issues. An on-demand version of the webcast will be available approximately 1 day after the webcast and can be accessed using the same audience link that was sent to you earlier. Now I'd like to introduce the presenters for today's webinar. Dr. Jens Rafelson joined EDAX in 2014 as an applications engineer specializing in EDS. He has a strong background in electron microscopy and has trained numerous students and clients in SEM and EDS theory and practice. His experience includes several years as the technical supervisor of the cleanroom facilities at Aalborg University in Denmark, where he applied a variety of techniques including SEM, FIB, CVD, PVD, PES, AFM, laser spectroscopy, and optical, electron, and ion beam lithography. Jens earned his PhD in physics from Aalborg University. His research focused on germanium surfaces and nanostructures probed by nonlinear optical measurement techniques, photoemission spectroscopy, and electron microscopy. As an applications engineer, Jens enjoys the versatility the position has to offer, ranging from training first-time users and running reference samples to discussing applications with experts in the field and developing new techniques to solve complex problems. He is highly interested in novel applications, expanding the areas in which EDS is traditionally used, and ensuring users and clients receive the training and information they need to solve their daily tasks and make the most of their equipment. Our second speaker, Dr. Shangsheng Mu, joined EDAX in 2018 as an applications engineer. Working out of the Draper, Utah office, he is responsible for providing technical expertise, conducting demos, teaching training courses, and after-sales support. Shangsheng also performs testing and validation for the engineering department and provides support for the marketing team. Prior to EDAX, Shangsheng was the lab manager at the Southeastern North Carolina Regional Microanalytical and Imaging Consortium in Fayetteville, North Carolina. Shangsheng graduated from Chengdu University of Technology with a Bachelor of Science in Material Science and Engineering. He earned a Master of Science in Material Science and Engineering from New Jersey Institute of Technology. Shangsheng completed his PhD in Earth Sciences at Boston University. Now over to Jens.
Thank you for the introduction, and evening, morning, afternoon, wherever you are, to anybody who has joined us. We'll start by just doing a quick outline of what we'll be talking about today. I'll start off by talking about X-ray generation in general. A lot of the stuff we will be discussing is around the background that we see in the spectra. So where does the background come from? And then we'll talk about what we can actually learn from the background. One of the big things that's easy to extract from the background is the Dwayne Hunt limit and if the sample is charging or not. We get into a little more detail then of the background signal where we need to talk about the geometry inside the system, how that affects the background. And then we'll move on to how to model the background. There's a few different options that apply at EDAX. There's, of course, other options that other vendors apply. And after that, we'll hand over to Shangsheng, where he will go through some of the examples showing these changes or anomalies in the background and a few things about what can be done to basically get around the problem, or at least figure out what the problem is. And we'll end up with a summary before we go into the. So, first off, this is a EDS spectrum, and we have background signal in here, which is the low flat part of it, flat-ish at least. And above the background, we have the characteristic peaks protruding. The background itself is generated by electrons being accelerated or decelerated in the sample, basically changing direction, whereas the characteristic peaks are generated by transition between the electronic states and the atoms in the sample. Most of the time, we're only concerned about the characteristic peaks, but today's talk we'll halfway ignore those and concentrate on the background signal. Should be noted, depending on which EDS system you're using, you may or may not see the background signal. There are cases out there where people use electronic filters to just remove the background or do software removal of the background before you see the spectrum itself, so you only see the characteristics. And we would like to point out today why, in our opinion, that's a bad idea. You actually lose a bit of it. But the background itself, the fundamental parameter is that any charged particle undergoing acceleration will emit radiation. So if we have a nuclei with the electron shells around them, and we have an electron coming in, so the red line here is the path of the electron. You have a negatively charged particle, and you have a positively charged nuclei, so you have Coulomb interaction between them. And depending on how close the electron gets to the nuclei, you will have more or less force, more or less bending of the trajectory of the electron. Whenever the electron changes direction, that is being accelerated, decelerated, it will emit radiation. This is what you use in synchrotron radiation and things like that as well. And we can describe the radiation that's emitted by Kramer's law. That's what we have. Basically, it depends on the atomic number of the sample, that is charge of the nuclei, a couple of constants. It depends on the energy of the electron coming in as well. And if we plot that out, it will look something like the blue curve we have down the bottom left. Now, if we compare that to the blue curve we have here in our EDS spectrum, we can see they are not really that alike. And the big difference here is that Kramer's law describes what is emitted by the electrons as they change direction. What we see in the EDS spectrum is what actually gets to the detector and is detected through electronics. So there is a difference there. This, as we said, is what is emitted. What we use most of the time to model the background is what we see here. If you look at it, it's basically a series expansion of Taylor's law, but it takes the absorption into account, and we see the red curve here on the left. When we use our model with absorption, we get something that looks much more similar to what we would see in an EDS spectrum. So the important part here is that the background shape itself depends on the landing voltage, the incident beam energy, how much energy we have in the electrons as they hit the sample. It depends on the sample self-absorption, and this is an important one. Kramer's law describes what is emitted, but it has to make it out of the sample again to the detector before we can actually detect it. So a lot of these X-rays will never make it out. You see Kramer's law says we'll have a very large number of very low energy electrons, but those are very easily absorbed, so they will never make it out of the sample, and that's why we see the sharp drop-off in energy when absorption. And it also depends on the detector itself, the detector efficiency. This includes the window transmission. One thing to notice here is the incident beam energy, E0. If we look at these equations, we can see that we cannot have any X-rays generated at higher energies than the incoming energy or the landing energy. And that is what we call the Duane-Hunt. Basically, you can't get more energy out than you put in. And this becomes quite important. This is the easiest accessible piece of information you find in the background signal. So if we have a charging sample, We shoot electrons down through the electron beam. They spread around inside the sample. This is a Monte Carlo simulation of electron trajectories using the Casino software. But if the sample is non-conductive, all of these electrons that we put down, they can't move around freely. So you basically end up with electrons stuck inside your sample. If you have a charged particle, you will have a field. So we have negative particles stuck inside the sample, meaning we get a negative electrical field. And we have a negative particle we're trying to put through this negative field. It means it will basically be retarded. You lose energy and you reduce the landing voltage that the electron hits the sample with. There's various tricks to get around it. The one we will use here is variable pressure mode, where we let a little bit of gas into the chamber, and the gas molecules hit the surface and carry some of the charge away. And you can get rid of this charge buildup. So this is an example of a quartz silicon dioxide in high vacuum and then increasing levels of variable pressure or pressure inside the chamber. So you can see at high vacuum, the black line, you have a very low silicon peak. And as we increase the pressure, this silicon peak tends to increase. What we see here is a change in the ionization cross-section. The probability of ionizing ionizing an atom, hitting out one of the core shell electrons, depends on the binding energy relative to the incoming energy of the electron. And in reality, we're changing the landing energy of the electron by changing the variable pressure state. We can see this in the background. So we had Kramer's law telling us the Duane-Hunt limit, the cutoff of the background. And we can see here at the high vacuum conditions, we have the black line, which is below 5 kV. We have a lot of charge buildup. This is a 15 kV spectrum. So basically you have about 10, 12 kilovolt charge buildup on the surface of this sample. So you have low overvoltage, thus you get poor excitation of the silicon. As we move up in pressure, you can see this background tail moves further to the right, moves further towards 15 kilovolt, and your silicon peak corresponding. So we know what the Duane-Hunt limit is supposed to be, and we can establish that by looking at this tail of the background. So here I can establish my E0 roughly by drawing the red line we have here. And in this case, the landing voltage is supposed to be 15. That's what we put down through the electron column. But because of the charge buildup of the sample, in reality, it's closer to 3.3. And it's important to know here that anytime you click the quantification button, we need the acceleration voltage to calculate the correct number to do all the math. We can't really know if there's any charge buildup on the sample. We only get the acceleration voltage as it's provided to us from the microscope. The microscope tells us I have 15 kilovolts of high acceleration, high tension going down through the column, so my landing voltage should be 15 kilovolts. If we put that into our model, we get very, very bad results. You can see here it says it's 91 atomic percent oxygen, 9% silicon. This is a quartz sample. It's supposed to be SiO2 or 6733 roughly. But you can see if I change my model or change the input parameter to my model based on the background tail here and tell it in reality I have 3.35 kilovolt and not 15, we get numbers that's much closer to the true stoichiometry of the sample. So if you have a charging sample, you can see it in the background. And in general, you don't want to click the quant button on, when you have a charging sample because the input parameters to the model are wrong. You would want to change the acceleration voltage to be the true landing voltage that's done here to get more reasonable results. So the Duane-Hunt limit is the easy one to extract from the background spectrum. To get into a little bit more detail, we need to talk about the geometry inside the system. So we have what we call an elevation angle, which is the angle between horizontal and detector normal. This is fixed whenever your detector is installed. It has nothing to do with the sample or anything like that, and generally it can't be changed. There's a few systems with it up and down. We then have the intersection distance. This is the distance in millimeters between the pole piece where the electron beam intersects with the detector normal. So again, this is a pure geometry thing. It has nothing to do with the sample. Typical intersection distances are 10 millimeters on most systems. If it's a FIP dual beam system, then it's typically about 5. There's some that's 15. There's some that's 8.5. This is all microscopic. Then we have the working distance. Now this is what you change with the focus knob on your microscope. This is the distance between the pole piece and the sample surface. This has nothing to do with the EDS detector really. The takeoff angle is the angle between the X-ray trajectory and the sample surface. This is where we combine the geometry of the detector with your sample. So the takeoff angle is an important parameter in all our calculations. And it's a combination of the detector angle, the position of the detector, the working distance of the sample, and the sample. So if I have my sample right at the sweet spot, my intersection is equal to my intersection, my working distance is equal to the intersection. Takeoff angle will be equal to the elevation angle. If I tilt my sample towards the detector, now my takeoff angle is larger than the elevation angle. And if I move my sample down, so my working distance is longer than my intersection distance, again, my takeoff angle will be larger than my elevation. This is important because this comes into play when we talk about the sample self-absorption, and we saw that was one of the parameters in our background model. So again, we have an electron coming down, we scatter around, generate X-rays, and if we have an X-ray up here versus an X-ray down here, these will have very different path lengths inside the sample and correspondingly different absorption probabilities. We can calculate the absorption probability by knowing the density of the sample, integrating over the depth in the sample. We need to model the depth distribution of the X-ray generation, and we need to know the attenuation coefficient and the takeoff angle. We know what the working distance is, and ideally the tilt of the sample. So the takeoff angle we can calculate in order to do the math. So integrating over the phi rho c is the number of generated X-rays, and then we scale it by the exponential function, which is the probability of them being absorbed. So essentially, the absorption probability depends on the takeoff angle, or in another way to say it is the path length inside the sample. So if I have an X-ray generated down here, and I now tilt my sample, we can see I changed the path length inside the sample, which means I reduce the attenuation length, which means I reduce the absorption. Low energy X-rays are more easily absorbed, so a tilt gives you bigger effect in the low energy range. You see a relative increase. And we can see this in the background. This is an ITO sample, indium tin oxide. I tilted it to between 0 to 50 degrees in various steps, and when you look at it from zoomed out, you don't see much of a difference. But we look at the detail of the low energy background. You can see here, as we tilt, the entire signal goes up. This is normalized to the high energy tin peak. But you can see both the characteristic peaks and the background levels increase as we tilt the sample. Same thing will happen if we go to longer working distances. As I go to longer working distances, I change my elevation angle, which means I get less absorption, which means I get more low energy X-rays. Relative increase in the low energy X-rays, high energy. This shouldn't affect the background tail, but there is I just want to point out one thing here. If you look at this background tail, see most of them trail off nicely towards 15 kilovolts, my extraction voltage. I don't have any charge buildup. But if you look at the very long working distance, 25 and 30 millimeters, you can see I have a bump starting to develop at the high energy range. This is backscatter electrons. This is bad for all practical purposes. This is because I'm so far away from the ideal geometry. This is a detector designed for 8.5 millimeters. So you can get artifacts in here. Basically, it's because the angle of the backscatter electrons coming in, you don't get sufficient trapping in the magnets in front of the detector. So if you go very far away from ideal geometry, check the background tail again, you may see backscatter electrons, which again means you're not going to have ideal modeling. So charging can be seen in the tail, as can backscatter electrons, whereas this tilting geometry mostly affects the low energy part of it. And we can take advantages of this. This is a sample where I have it at 0 degrees tilt, and we can see if I give the background model an input of 0 degrees tilt, I get the blue line here, which matches quite nicely. If I give the input of 50 degrees tilt, we can see I get an overestimate of the background. So depending on whether the sample is tilted or not, my background signal will change, and I can adjust the model to basically determine how much is that change. So if you have an overestimate of the background, the model overestimates the background, that means the sample is tilted to the relative to the expected geometry. Conversely, if you have an underestimate, it also means it's tilted just in the different direction. But in principle, you can estimate the tilt by modifying the input parameters to the model. We have a couple of different ways we model. Right now, I've talked about the true Bombshell model, where we use a full physical model. Another approach, what we use in our Apex software, is what we call the Snip Routine, statistical nonlinear iterative peak clipping. I will point out that's not a marketing term we came up with. That's the actual term they use in the original paper down here at the bottom. So the difference between these, here I have a multi-sulfide. If you look at it from far away, there's not much of a change. But if we zoom in and look at the background, you start to see something different. Snip is just a smooth curve, whereas the Bombshell has absorption lines and everything else. The advantage of the Snip is that there's no user input. No matter what you do, you'll always get the same results. You'll get good fit on all samples. Whether it's a tilted, fracture surface, particles, whatever it is, you will always get a good fit with the Snip. Background includes absorption lines. In a lot of ways, it's a more precise model. Sometimes it will give you a bad fit. That's not a failure of the model. It means that your sample does not match the input parameters, which means don't click the quant button because something is wrong. Using the Bombshell model, you can extract information about the tilt of the sample, self-absorption, electron artifacts, and like that. So here's an example where I would probably prefer to use the Snip model. This is my Bombshell model. This is a very non-ideal sample. It's a piece of a tube. I'm down in the middle. It's a very rough surface. And my Bombshell model, you can see, underestimates everything. So yes, this one's probably tilted towards the detector. But it's hard to see what elements are really in here. It's hard to make a qualitative analysis of this sample. Whereas the Snip, where the background may not be perfect, or from a theoretical point of view, but neither is the sample. But since it does give you a good fit, it's much easier to see now where do you actually have the characteristic peaks. So the qualitative analysis is much easier with something like this. So both of these models have their advantages and disadvantages. With that, I'll hand over to Xiang Mu, who is going to go through a few examples of different problems you can see in the background with different samples.
Thank you, Jens. Hello, everyone. I'm gonna show you some real examples. And this one in this is EM image. Those are randomly distributed alumina particles. This is the normal spectrum of alumina. This spectrum is from the spot in the top right of the image. We see the low energy shows very stronger absorption. If we move the beam to the left, we see significant increase in misfit or low energy absorption. If we move the beam further left, we see all of the low energy peaks and the background in the low energy range have been pressed down furthermore. Here we look at the background tail. We see the background tail ends at 15 keV. The acceleration voltage we used was 15 keV, so that means there is little to no charging. But there is strong attenuation below roughly 8 keV, so this background looks very abnormal. In a normal background, we should see a hump in the low energy range, and then it curves down nicely towards the tail. So what happened to this sample? If we look at a larger area, we see the area of interest is actually below a large particle. The CPS map shows the area of interest is in black color. The CPS map is count per second map. It shows you the X-ray count rate and each pixel. So that means the brightest part is where the X-ray count is the highest, and the dark or the black part is where there is a little to no X-ray count. In this case, the CPS map shows the area of interest is heavily shadowed by the particle, so that's why we see the strong absorption in the low energy range. Note that, and also from this CPS image, we can figure out the detector direction is to the top right based on the shape of the shadow, the black area. Note that detector direction is microscope dependent, so it can be any direction depending on where you mount your detector. These blocky crystals are galena. I analyzed 2 spots on top of them. The upper spot is from the piece that is bumped up, and the lower spot is from the surface that is one step down, and the detector direction is to the top right. So that means the lower spot is in the shadow zone of the piece that is bumped up. We look at the spectrum from these 2 spots. Line outline is from the lower spot. We see the background in the low energy range is very low. That's due to the low energy X-rays are subject to strong absorption by the piece that is bumped up. We also see higher carbon and oxygen peaks than the non-shadowed spot. This is due to fluorescence. In the high energy range, we see the shadowed spot has a bump. This is because the high energy X-rays can still travel through the piece that is bumped up. They do have enough energy to do that. Here in this CPS image, we see there is a black triangle. So this area is consistent with the shadow zone we interpreted. This black triangle also confirms the detector direction is to the top right. To get rid of the shadow effect, you can rotate the area of interest to a direction that the X-ray path is not blocked. Now I have this sample rotated, and I collect a spectrum from the surface that is previously shadowed. In the spectrum, this is line outline. We see the previous shadowed spot shows a normal background right now. you may notice that the background in the low energy range of the shadowed spot is a little bit higher than the spectrum from the higher surface, and also the carbon peak is higher. This is due to the lower surface is tilted a little bit towards the detector. So this results in a takeoff angle change. I'll mention this in next slide. And this sample shows topography. This is galena as well. From right to the left, we see the surface curves up, becomes flat, and then curves down. So the three spots on this sample, they represent the surface that is facing towards the detector, the flat surface, and the surface that is tilted away from the detector respectively. And I overlay the three spectrum together. We can see red color is the spot from the surface that is tilted towards the detector. We see it has the highest carbon peak, highest background in the low energy range. That's because this surface, the surface facing the detector, it has the highest takeoff angle. So that means the shortest attenuation length. So there's less absorption of the lower energy X-rays. The orange outline is from the surface that is tilted away from the detector. We see it has the lowest background in the low energy range, also the lowest carbon peak. This is because this surface has the lowest takeoff angle. That means the longest attenuation length. So there's more absorption on the low energy X-rays. And we see the flat surface, the spectrum from the flat surface is the cyan outline, so it shows a normal background and a normal peaks. And the cyan outline is in between the other two. Now we model those backgrounds for the spot from the surface tilted towards the detector. We see the background is underestimated. For the flat surface, the background model fits the background pretty well. For the surface tilted away from the detector, we see the background is overestimated. So that means if you see your background model does not fit your background, that's an indicator that your sample surface is not flat. And if you do quantification analysis, the results will not be good. Now I want to mention challenges in particle quantification. And I'm going to use some examples to show you how to identify the cause of the variation and the effects of scan strategies on the particle quantification. While we are doing quantitative analysis, we use the K ratio as the basic approximation. Although K ratio is a good starting point, it does not take absorption and interactions between the elements in the sample into account. So in order to make your results more accurate, we need to apply ZAF corrections. ZAF corrections make three assumptions in this equation. This is the equation of absorption. You have seen this equation on the slide, sample self-absorption. So ZAF corrections assume the sample is homogeneous, assumes the sample is flat. That means if your sample has topography, then there are additional absorption take place after the X-ray reaches the sample surface. It also assumes the sample is infinitely thick as seen by the electron beam. That means all of the energy is deposited inside the sample. When we satisfy these assumptions, the quant results should be pretty good. But the reality is our particle samples usually do not meet all of these assumptions. Particles are not homogeneous within the interaction volume, infinitely thick to the electron beam. Here I'm showing Monte Carlo simulation of the electron scattering on the left-hand side and energy deposition on the right-hand side in a bulk alumina sample with 15 keV of acceleration voltage. On the left-hand side, we see the incident electrons penetrate more than 1 micron into the sample. On the right-hand side, the cyan outline is where the electrons have 5% of energy left. So from this, we can interpret the cross-section of the interaction volume is about 2 micron by 2 micron. That means the interaction volume is on a scale that is comparable or even larger than the particle size. If your particles are relatively fine-grained, that means not all of the energy are deposited inside your particles. Particles have effects of topography. Large particles may create a shadow zone for smaller particles. On the left-hand side, we see the X-rays from particle B do not have a path to the particle. The count rate would be very low at particle B. An even worse scenario is on the right-hand side. There's a big particle, particle C, adjacent to particle B. And X-rays from particle B may excite particle C due to fluorescence. And X-rays from particle C have a path to the detector. So we think we are analyzing particle B, but actually the composition is a combination of particle B and particle C. Particles are also of random shapes and sizes, resulting in takeoff angle change. Here I'm showing 3 spectra and 3 different locations on the same particle. From location B, this is a flat surface, so it shows a normal spectrum. And location C, where it has the highest takeoff angle, so there is the shortest attenuation length. That means there's less absorption of the low energy X-rays, so we are expecting a higher low energy peak. On the other side, at location A, it has the lowest takeoff angle. So that means the X-rays have to travel all the way through the matrix to reach the detector. So they are subject to more absorption. So we should see a lower low energy peak. The experiment, we used pure standards that have been ground into particles. We used a Zeiss SEM with EDAX Octane Elite EDS detector for spectrum collection. Acceleration voltage was 15 keV and 2 life seconds collection time. To baseline the quantification, the composition of the particles, we did multiple measurements on a large flat grain for each sample. For the outer particle spectrum collection, we collected 100 particles per sample using 3 different strategies. For raster scan, it's from a raster covering 80% of the particle core. For particle centroid, we park the beam in the geometric center of the particle. For centroid track, the beam is placed at the brightest or darkest grayscale point of the particle. So for each sample, we did raster scan 2 different types of single point acquisition. The mean compositions of the measured particles are within 0.1 to 3.2 weight % of the large particles, the large grains. In this table, the first row shows the deviations from the large flat grain, the true composition for raster scan. Second row shows for centroid. The third row is for centroid track. We see single point acquisition is worse than the rest acquisition. To figure out the cause of the variation, I look at some particles that have very bad quantification results. In this case, this small particle, this small circled particle, it has very low oxygen concentration. The detector direction is to the top. We see on the X-ray path, there is a bright big particle. So that means this circled particle is sitting in the shadow zone of the large bright particle. Here in the spectrum, the non-shadowed particle is in red, and those outliers are from the shadowed particle. We see there is a very strong attenuation of the oxygen peak. We look at the background of the shadowed particle. We can figure out in the low to mid energy range, the background is very low. That's because all the low energy X-rays are subject to strong absorption by the large bright particle. In the high energy range, shown in a smaller spectrum, we see the red color is from the shadowed particle. There is a hump in the high energy range. So that's because the high energy X-rays still have can still passing through the bright particle. The other root cause is change in takeoff angle. Particles have topography that results in the takeoff angle change and leads to deviations in the quantification results. For this category, I look at the weight percentage of low energy elements for each sample. I circled those particles that stand away from the mean weight percentage line and look at them closely. Here is one example. The detector direction is to the top. This particle is still facing towards the detector. Look at the analysis below. We see this particle has a higher fluorine concentration than the single large grain, which is the true composition. In the spectrum, we see the particle tilted towards detector has higher fluorine peak. That's due to the higher takeoff angle, so less absorption of low energy X-rays. In this case, from the ITO sample, the detector direction is still to the top. We see this particle has multiple surfaces forwarding two different directions, but in general, most of them are facing towards the detector. In the analysis below, we see the particle has higher oxygen concentration than the single large flat grain, which is a true composition. And the particle centroid track has even higher oxygen concentration than particle raster scan. In the spectrum, we see the particle flat. The red outline has the lowest oxygen peak and also the lowest background. And the particle towards detector acquired by centroid track, the orange outline has the highest oxygen peak and highest background in the low energy range. For the particle raster scan, the sign color, the peak height, the background height is in between the other two. So why this happened? We look at the two small images in the middle. The top one shows the raster scan covers the entire area of the particle. So that includes surfaces tilted towards the detector and surfaces tilted away from the detector. So the effects of topography are somewhat canceled out. And for the particle-centroid track, we see in the bottom picture, the beam was actually placed on the surface that is tilted towards the detector. So that means a higher takeoff angle, less absorption of low energy X-rays. So we see a very high oxygen peak and background. This example shows us why raster scan has less deviations than center spectrum collection. Now I'm handing it back to Jens for the summary.
Thank you, Shang. So what we would like for you to walk away with today is that the background does have quite a bit of useful information in there. The most readily accessible one is the basic charging of the sample. Look at the tail of the background, and it should trace off nicely towards your acceleration voltage. If it doesn't, that means you have charge buildup, and you can actually estimate the amount of buildup simply by looking at where does the tail end. That gives you two options. Either get rid of the charge buildup somehow, coating the sample or variable pressure mode, or be aware that you have charge buildup, and you can get somewhat reasonable results by changing the input parameters to the quantification model to accommodate for the charge. Also, any changes in takeoff angle will give you deviations in the background modeling and quantification results. And you can also see that in the background, in the low energy range. It's a more subtle change, but it is there. If you tilt the sample using the microscope stage, that shouldn't give you any problems because we read that tilt value. We have that as an input parameter to our model. The problem comes when the sample is tilted and the EDS software does not know about it. So if you have, as Shang showed, samples where you have surfaces that are tilted towards or away from the detector when the stage is flat, that will give you deviations. And if you use the Bombshell modeling, you can see that as an over or underestimate of the background, depending on the tilt angle. Using the Bombshell model, you can get a lot of information about what's going on in the sample, and it can help you in troubleshooting, but the essence of it is that if you don't have a good fit with the Bombshell model, that's usually an indication you don't have good conditions for quantification. A bad fit doesn't mean a bad model. We're not saying our model is perfect. Of course, that can't be the case, but most of the time it will indicate that your sample does not meet the expectations that we have in the model in order to do good quantification. The Snip model is a simpler approach, and this is more similar to what some other vendors do with just using a math filter to pull out the background. It can have its advantages, mostly for when you're doing qualitative analysis, not quantitative, but qualitative, just figuring out which elements are in there. Just using a math filter and not caring too much about the perfect modeling constraints can make it easier to see if you have a peak above background. For any of the tricky samples, particles, fracture surfaces, things like that, you have to be aware that the quant assumptions are not valid, which means you can get significant variations from the true composition. It may or may not matter. That depends on what your actual goals are, but be aware that in general, any particle, you will not get good quantification. And even if you have flat particles, keep a lookout for what's around. We gave some, often this is obvious when you zoom out on the microscope, but if you're searching around at low magnification, you may not notice that big particle right next to the smaller one. And the background tail will give you information about additional absorption outside the particle. So be aware about the shadow zone problem. And again, which direction the shadow goes, that depends on where your detector is mounted. Shadowing is usually not too much of a problem once you realize it is there. Simply rotating your sample 90 or 180 or whatever it requires can solve the problem most of the time. And with that, we are done with our presentation, and we will now go into our Q&A session. And I see we already have quite a few questions in here. One of them we have here is, you should just run spotted samples for EDS analysis. It's quite a good question, and it really depends on what you're trying to do. If you want to do true, precise quantification, no. The problem is you put another layer of material on top of your sample that the model typically cannot accommodate for. Any coating of samples, we always recommend carbon if you absolutely have to coat your samples. Just because it's a light element, you don't have too much absorption in there. If you use extremely thin metal coatings, it can be done, quantification or quantitative analysis, but you have to be very careful about thin layers, just enough to do charge compensation. Any thicker layers, any heavy metals can often create problems with additional attenuation, especially if you're looking at light elements. There is a question, the optimum takeoff angle. That will depend on what you on your geometry, basically. There is such a thing as an optimum takeoff angle. Usually that's at the design distance of the system where you get the most counts going to the detector. But that being said, there's nothing wrong with having a takeoff angle that's away from the optimum. It depends on what you're trying to do. Often you may want to tilt your sample, or if you're doing EBSD, you will have to tilt your sample. You may have a large sample mounted in your holder otherwise, where you need to drop the stage down to accommodate for the large sample. So in that case, you can run analysis at other takeoff angles, and as long as we know what the takeoff angle is, it's not a problem. But if you have a sample that's tilted and we don't know that it's tilted, then you have an offset in what we think the takeoff angle is and what it truly is. That's when the problems occur. Typical takeoff angles are often about 35 degrees, but you do have special systems where it's a more shallow takeoff angle depending on what the exact application is. There is a question on slide 8. Back and pull out that slide. Should be this one. Can you repeat the way in which you calculate the voltage due to charging? Basically, I just look at the spectrum here. Let me animation. So we can see each of them has a drop-off where it goes close to 0. When you zoom it out, you can see it has a tail that goes down. And this is a rough estimate. I just take the black line here and see where does that tail roughly tend down towards 0 counts. And in this case, about 3 for 3.5 for the black line, about 5, 6-ish for the red line, and then the green line, we're up to about 12, 13, 14 for the blue, and 14, 15 for the red. So in this case, it's just a visual estimate. You can do a model to it, but in reality, it gets a little tricky because often you have low count rates when you go all the way out. So you can model it, but the error margin will be pretty large. So I just kind of squint and look at it and say it's about that. There is a question about, does it matter what background modeling we're using? We have an old machine with non-mechanistic modeling. Depends. Depends on what you're trying to do. If we go and look at this slide out with my moly sulfide. So in something like this, most of the older systems will just do a straight line fit through the peaks to establish the background. And if you're in the high energy range, it doesn't really matter that much. A straight line fit is very close to the real model. You can see our Bombshell model, you have the two bumps underneath the peak towards the high energy side. That's the absorption lines for moly and sulfur. So in that case, for high energy peak or relatively high energy, it doesn't really matter much. The problem can come when we go to the low energy range. We have something like this. Again, this is not an ideal sample, but just for illustration purposes, and this addresses one of the other questions that was in here. We can see here in the low energy range, there's a lot of modification to the Bombshell background as you start to hit the different absorption lines inside the sample. And in low energy range, it's very important to have the absorption modeling correct. So using a linear fit in the low energy range can create issues depending on what kind of absorption you have down there and how precise you're trying to do quantitative analysis down in that range. We can see the Snip model relative to the Bombshell model tends to overestimate the background a little bit under the peaks because of the way the filtering works. Whether it's a true issue depends on how precise you're trying to model your sample. If you are really trying to be very precise in the low energy range, most of the time we would recommend using standards instead of relying on a full standardless modeling approach, and that will resolve some of these problems. There's another question about manual corrections by fitting the background. That is an option we have in the software, and again, it depends on what what you're really trying to do. It can be a slight change in takeoff angle, for instance, and a few degrees. Often you can see it in the background. Within the error margin, it doesn't really affect anything for the quantification routine. There's also a question about quantification reliable for peak to background based CF algorithms in the same question. The peak to background based algorithm has the advantage that it's inherently normalized, which means you will get a total sum percentage. If that adds up to 100, you can be pretty sure your geometry is very close to the ideal. The peak to background based algorithm, though, does not really apply to elements lower than manganese, basically. At that point, the peak to background model is not particularly good, so it's mostly for the high energy backgrounds, and it's mostly in the low energy you will have to adjust the background. But if you see a significant misfit in the background and you have to do a lot of fits to make the background look nice, that's usually an indication you shouldn't trust the quant results with particularly high precision. But again, it depends on what you're trying to do and what level of precision you are looking for in the quantification. This is, and some of the, push that slide out. Here we have the background on the left-hand side extending very far up, and there's a question of why does that happen? This is pretty much because we're down in the low energy range. This is what I was addressing with the molysulfide sample as well, where we have a flat background. There's very little absorption in the high energy range, but down the low energy range, you get a very high degree of absorption. And what we're seeing here is that you have quite high absorption, but then you see all these steps in the background, and that's as soon as you go below the absorption line for a given element, then the transmission through the sample goes up. So this is, we have quite a few things in here. There's some tin, and there's copper, there's carbon, and various other things. Each of those will give you a jump. And when you go below that, you get that increase in the background. That's what we're seeing here. And you don't see that in the high energy range because absorption is not as pronounced in the high energy range. Okay. See, we are running short on time here. It's just about to wrap up. I think do have time for at least one more. There's a question here about X-ray fluorescence, why we get higher carbon and oxygen. So basically, we have X-rays being generated in the shadow region here. This one is actually the tilt, but the previous one we had the absorption. So if we have X-rays being generated down in the shadow region, to get to the detector, they will have to go through a piece of the sample that's sticking up. When X-rays pass through material, there is a probability of the X-rays being absorbed. And whenever an X-ray is being absorbed, there's a chance of those knocking out a core shell electron, and we create a new X-ray. Basically, we have a conversion of a high-energy X-rays to a low-energy X-ray, which is X-ray fluorescence. So we can lose some of the high-energy stuff and gain some of the low-energy stuff. In this case, we see all of these are scaled to the lead sulfide, so we won't see the reduction, but we see we get an additional gain of carbon and oxygen. The fluorescence correction is quite common, and it is taken into account in the CAF corrections or various model that all the different vendors use. So it is a known process. It is something that can be calculated. The issue is when we have topography and absorption outside the sample, we don't know what the material absorbing is, thus we can't calculate fluorescence absorption corrections once the X-rays leave the sample. So fluorescence in and by itself is not a problem when all the other restraints of the quantification model is met. It's when absorption and fluorescence happens outside what we believe to be the spectrum area, then it becomes a problem and you can get relative changes. I think we are out of time, so we will wrap up for today. We still have a few questions. We will answer those by email as we get them in our mailboxes. And just as a quick comment, we have another upcoming webinar on EBSD on October 24th by Matt Nowell, our product manager. And he will be talking about EBSD data collection, how you want it in our new Apex software. And with that, thank you for joining us today, and thanks for your attention.